Okay, we're now on chapter 9, Birational Maps and Blowing Up. Alright, so to introduce this chapter, let's recall that we've seen examples in this class of varieties that are almost the same in the sense that they contain dense subsets, open dense subsets that are isomorphic, but the varieties themselves are not isomorphic. So let me tell you what I mean. So for example, we had A2 as a dense open subset of P2. Okay, so there's a open subset of P2 that's isomorphic to A2, but P2 is not, P2 itself is not isomorphic to A2. And similarly, if we look at P1 cross P1, that has an open subset isomorphic to A1 cross A1, which is isomorphic to A2, right? All right, so now here we have three things. We have P2, we have A2, and we have P1 cross P1. No pair of those is isomorphic, but they all contain a copy of A2, which is isomorphic. Okay. All right, so that's one example. That's just in this last chapter, we saw that the Gathmannian had an affine subset like this, Gathmannian K and this is dense, right? Okay, maybe you see that as a generalization of part A. Let's look at one more example that's maybe just a slightly different flavor. So remember we had, back in chapter 4, we had this thing. So let me just draw the picture because that's maybe the most memorable block part of it. So we had A1 mapping to the vanishing locus of x squared minus y cubed. Okay, and remember this one was, this is an isomorphism on A1 minus the origin. So maybe I should say from to this vanishing locus here minus the origin. All right, so if you take out the origin and this point here, this is actually an isomorphism, but it's not an isomorphism from A1 to v of x squared minus y cubed because there's a singularity here. This is different. It's not the same thing, right? It's there and there. Okay, but it is an isomorphism on an open subset. Okay, so that's an example of this kind of thing. All right, so we're going to study this sort of phenomenon and talk about what things are the same about varieties like this and what things are different. And that'll be kind of one of the themes of this chapter. Okay, so here's our first definition. So let's let x and y be irreducible varieties. Then a rational map f from x to y. And usually we write irrational maps with a little dotted arrow like this. So this dotted line here means that it's a rational map from x to y. And what is a rational map? It is a morphism from an open subset of x. To y. Okay, so let me write it like this. F goes from u to y. Okay, and we use the same letter to denote this morphism as we do the rational map. That's very common. And we also say that two rational maps let's say u1 to y and f2 is u2 to y, where u1 and u2 are open subsets of x. These are considered the same. If F1 is equal to F2 on some non-empty open subset V in the intersection. Okay. So this actually does give an equivalence relation. So you can think of a rational map as an equivalence class of maps on these open subsets of X. Now, let me also remind you we're dealing with irreducible varieties. So any open subset of X is actually a non-empty open subset is dense. So rational maps do give quite a bit of information about X. If you're thinking about manifolds, then or you just have like a tiny open ball or something, it doesn't seem like a lot. But for irreducible varieties, this is giving a significant amount of information. Let me give you also just one quick remark that in the case that F1 is equal to F2 on V, then actually F1 equals F2 on all the common domain of definition, right? All right. Why is that? Well, we had a lemma a while back that the locus where two functions agreed should be a closed subset. So if they agree on an open subset, they must agree on the whole thing. Okay, so that's what we had. Okay, here's one more remark. In general, composition of rational maps doesn't make sense. Right, I mean, the problem that can happen is, what if I had a f from x to y, where all of f of x mapped to a single point, right? So was contained in a single point in y. Okay, and then what if you were trying to, take a g from y to z, but you couldn't find any representative of g that included a point, right? Maybe all the representatives for g were open subsets that didn't contain this point, then there'd be no way to define the composition. Okay, and then I'm talking about rational maps here, so let me put some little dotted lines here. Okay, so composition doesn't work in general, but you can add an extra hypothesis to make it work. So here's a definition. So f, a rational map from x to y, is dominant if the image f of x contains a non-empty open subset of y. All right, and in this case, we can define the composition. So if g from y to z is a rational map, then the composition do f first and then do g is a well-defined rational map. All right, maybe I'll let you think about the details, but there's nothing too complicated going on. The other thing maybe you want to check is to make sure that this condition here of being dominant doesn't depend on which representative you pick for f, right? F is is actually an equivalence class of maps, but whether or not it's dominant doesn't depend on which representative you take. And then you need to think just for a moment about why this composition makes sense. Okay. Okay, and then part B of the definition will say that if we have a rational map that is dominant, and there is another dominant rational map, going the other way. So in this case, it makes sense to do the composition. So the f of g equals the identity on y, and g of f is equal to the identity on x. Then we say f is birational. A birational map. We say x and y are birational to each other. All right, so this is something kind of like some analog of isomorphism, but weaker. So all the examples that I gave in the introduction here. So P2 is birational to P1 cross P1, and is birational to A2. And the Gathmann is birational to an affine space, and A1 is birational to this vanishing locus here. Okay. And here's a good observation. So two varieties are birational. They have the same dimension. All right, so I think we had some exercise a while ago that if you looked at an open subset of an irreducible variety, then it has the same dimension as the variety. Okay, so this observation follows from that. Now let's do construction. It's important in the study of birational varieties. This can be kind of analogous to the coordinate ring that we did before. Okay, so a rational map from x to a1. Let's still assume that x is irreducible. And you can think of a1 as just being our base field k. Is called a rational function. On x. Okay, why is it called a rational function? So, I mean, let's just take, for example, if x is equal to an, then a rational function is just a quotient of polynomials, right? I don't know, something like x squared plus y divided by z plus x squared minus y or something. All right, so something like this is well defined on as a rational function on A3. It's not defined on all of A3, but it does count as a rational function because you can just subtract out the vanishing locus of the denominator, and that will give you a function on an open subset of A3. Okay, so if you like to call these rational functions before, that means the same thing. Okay, so another way to think about what a rational function is. So a rational function is just phi in ox of u for some u, an open subset of x, where phi1 and phi2. So let's say we had phi1 in. Oh, sorry, that is not px. This should be ox. The structure should. So if we had phi1 in ox of u1 and phi2 in ox of u2, I should consider these to be the same rational function. Rational function. If what? If phi restricted to u1 intersect u2 is equal to phi2 restricted to u1 intersect u2. So if they agree on the overlap, then they should be considered the same rational function. Let me just remind you again, for irreducible varieties, the intersection of two non-empty open subsets will be, again, a non-empty open subset, which is still dense, right? Let's call the set of all rational functions is called kx, and we'll call it the function field of x. All right, now the function field is in fact a field in the sense of algebra. Why is that? Well, I think it's easy to see that you can add things, right? So if you had a phi1 plus phi2, you can add them. You probably have to restrict the intersection, right? Right, I should say in OX of a U1 intersect U2. Okay, so that's no problem. Same thing for multiplication. Inverses or additive inverses are okay. The interesting part maybe is the multiplicative inverses. So if you want to define phi inverse is well defined on U minus the vanishing locus of phi. Right. The problem is in general, if you try to invert something, it might have a 0 in the denominator sometime. Or it might be 0 sometimes, so then you can't find the multiplicative inverse. But since we only need it to be defined in an open subset, we can just subtract off the vanishing locus of the section. And remember, that's a closed subset by a lemma we had earlier. Okay, and then once phi is not 0 anywhere, then the multiplicative inverse makes sense. All right, so we actually get a field here, and we'll call it the function field. And as I hinted before, this is supposed to be kind of analogous to the coordinate ring, except for when we're thinking about rational maps. All right, so let's make this observation kind of along those lines. So if U in X is non-empty open subset, again, and X is still an irreducible variety, then the function field of U is isomorphic to the function field of X. Okay. How does the isomorphism work? Well, let's just think about that for a second. So how do you map Ku, the function field of U? Remember, U is a variety because it's an open subset of a variety, to the function field of X. Well, if you have a phi in O U of V, where V here is an open subset of U, well then V is also an open subset of X. So we just map it to exactly the same function, now considered as being in the structure sheaf of X, right? And how does the inverse look? So let's call, I guess we'll call that F, and this will be the inverse, mapping from Kx to Ku. If I had phi in Ox of V, where V is an open subset of X, I could just map that to phi restricted to V intersect U, which is now an open subset of U. And so this lives in the structure sheaf of U. Okay, so it's not maybe too hard to check that that's an inverse. Okay, so if you have an open subset, and this is remember a dense open subset, then the function fields are isomorphic. So in particular, if X and Y are birational, then K of X is isomorphic to K of Y. All right, and then observation B is if X is affine, then k of x is just, and let's say irreducible. Then k of x is equal to just the field of fractions of the coordinate ring. So remember, if x is irreducible, then the coordinate ring a of x is an integral domain, and then this frac here means to take the field of fractions, right? Just allow yourself to divide by anything, and we're claiming that's isomorphic to function field. This follows from an exercise that I think we skipped, but maybe it's not too hard to imagine what's going on here, right? Basically, the idea is you can take any function here, but then you're allowed to divide by anything because you can always just exclude the zero locus like we did up here. So you're allowed to divide by anything, and that's basically what the construction of the fraction field. Okay, so you can think about that if you want to be more careful. Okay, now we're ready to give a construction of a certain class of birational maps. And this construction is called a blowing up. So blowing up is like blowing up a balloon, not like a bomb blowing up or dynamite or something. We'll talk maybe a little bit later and look at some pictures about why it's called blowing up. Okay, so let's do the first version of the construction. So we're going to start with an affine variety, x in an affine variety. We'll talk about later how to generalize this to general varieties, but we get most of the idea of what's going on just by looking at affine varieties. So let's say we're given polynomials f1 up to fr in the coordinate ring of x. We set U to be the open subset where these polynomials don't vanish. Okay, so that means there's a morphism from U to PR minus 1. Okay, we talked about how to construct this morphism in our chapter on projective spaces. Right, the idea is that the point x just maps to a point with homogeneous coordinates f1 of x to fr of x. I guess maybe the difference here is that our x and our u are not projective varieties, so we don't have to worry about making sure that the f's have the same degree. They can just be arbitrary regular functions, and then this point in homogeneous coordinates is sort of automatically well defined, right? Okay. So we have this map. Let's call it f, and let's look at the graph. The graph of f, and what is the graph of f? Let's remember, it's the set of all points x, comma, f of x, such that x is in U. And we're thinking of that as a subset of U cross PR minus 1. Okay, this is closed. A closed subset of the product. Remember, we proved that when we were talking about the separated property. So you have to use the property that the diagonal is closed, and then you can work out that that implies that the graph is closed. So you need these things to be varieties to make this work. It's closed in U cross PR minus 1, but it might not be closed in X cross PR minus 1. So that's going to be our definition here. The closure of the graph in X cross PR minus 1 is called the blow-up. Of x at f1 through fr. Okay, we will use the notation usually x tilde with a little wavy thing over it to indicate the blow-up usually. We should also note there is a projection map from x tilde to x. Where does that come from? Well, that's just the projection, right, from the product, right? So x tilde is a subset of x cross PR minus 1, and that has the obvious map to x there. Let's call this map pi. Maybe I'll call both of these maps pi. Okay, before we do some examples, we're going to make a few observations first. So the first thing to note is remember that gamma f, the graph, is actually isomorphic to u, right? Because just by the projection map, right? So pi restricted to gamma f, right? Because right in the first coordinate is just all the points of view. So if you just project it down, you just get all the points of view. Okay, so we can view U as an open subset of we're going to view U as an open subset of the blow-up. Why is that? Well, because the blow-up is defined as the closure of the graph, and the graph is isomorphic to U. So so that means, you know, if we identify U with the graph, then we have U as an open subset of x tilde, in fact, a dense open subset of x tilde. And in fact, pi, this map, now thinking about this map here, pi restricted to U is an isomorphism onto U considered as a subset now of x, right? Okay, so x tilde, the blow up, is birational to x. All right, the dense open subset that is isomorphic is the U, which is the graph here, and also the U, which is the subset that we started with as an open subset of x. If we now look at x tilde, the blow up, minus out this open subset that is isomorphic to an open subset of x, we take that out. The leftover stuff is called the exceptional set. So pi is probably not an isomorphism on the exceptional set. All right, so what you're kind of supposed to be thinking is we started with this variety x, and then we took out some stuff. We took out the vanishing locus of some functions, and then we made a new thing, x tilde, and x tilde is exactly the same as x on U, they're isomorphic, but on the vanishing locus of the f, we took that out and we put some other stuff in. we put this exceptional set in, and it's different than what you had in there before. Okay, so we'll spend some time talking about what's different about it and what it looks like and why that was a good thing to do. Let's think now of y, a subvariety of x. So this is kind of a new thing here. Let's think of y, a subvariety of x. Then we can blow up y at the same functions, f1 through fr, right? You can think of f1 through fr, you can restrict them or map them to the quotient and consider them as functions on y. And then, if you think about what happens, the blow up of y, this is a subset of y across pr minus 1. And we have the blow up of x cross pr minus 1. Okay, and this is also a closed subset right here. You can think about it for a minute and realize that y tilde it can be considered as a closed subset of x tilde. So the blow up of y is contained in the blow up of x. In fact, y tilde will be equal to the closure of y intersect u in x tilde. Right, so right now I'm thinking of u as an open subset of x and of x tilde. So then you can intersect it with y and get something, right? Because y is a subset of x. Okay, but now we're thinking of it in x tilde and taking the closure, and that will exactly be the blow up of y. And this is usually called the strict transform of y. Okay, if you want a little exercise, you just should think about why this is not equal in general to pi inverse of y. All right, so another way you could get move y into the blow up is to take the inverse image of y under the projection map of pi. But that will, in general, give you something different than strict transform. Right? In this case, you might get big chunks of the exceptional set, right? If y intersects the complement of u. Okay, let's do our first example. But sadly, this is going to be not very interesting example. So this is the trivial cases. Suppose r equals 1, so that means we're just blowing up at one function. Remember, we are blowing up at r functions, f1 through fr, but let's just blow up at one function. All right, then x tilde should be contained in x cross p r minus 1, so it'll just be p0. So remember, p0 is just a single point, so x cross p0 is just x, and and also the graph of our function f will just be isomorphic to u. All right, so x tilde will just be equal to the closure of u in x, right? Okay, so that's right. And remember, u is the vanishing locus, or the complement of the vanishing locus of the x. So if f1 is not equal to 0, then u equals x minus the vanishing of f1, and u closure is just equal to x. All right, so the blow up is just isomorphic to the original function. Nothing interesting happened. If f1 is actually the 0 function, then u is the places where the function doesn't vanish. That's just the empty set. So x tilde is just the empty set. Also not interesting. Okay, so in order to get interesting examples, we need to have, I mean, it all makes sense, but it's not interesting, but we need to have r bigger than 1. Before we see some interesting examples, we're going to want this lemma, which gives us a sort of a more concrete way to describe the blow-up. Taking closures seems kind of hard to work with, or to do computations with. So this lemma will help us out a little bit. So the blow-up, x tilde in x cross PR minus 1 satisfies the following relations. Okay, using the notation that we had before. X tilde is contained in the points x, y, and x cross PR minus 1, such that yi times fj of x is equal to yj times fi of x for all I and j in 1 through r. Okay, there we go. What's the proof here? So let's let x, y, and u cross PR minus 1 be any point in the graph of f mu to PR minus 1. As we defined before, remember, this f is just the function that's defined by all the fi's. Okay, then being in the graph exactly means that the y's are given by f's applied to x. That was the definition of the map f and the definition of the graph. Okay, but this condition here is equivalent exactly to these equations: yi fj of x, yj fi of x. Why is that? Well, how do you tell if 2 points of projective space are the same? Well, one way to do it is to put this in a 2 by r matrix and then take all the minors, and that will tell you whether they're linearly dependent. So that's exactly what we have here. Okay, and all right, now we can extend these equations. These equations make sense on x cross PR minus 1. So let me write that down. Minus yj fi of x. So we take the vanishing of all these equations, but now I consider them on x cross PR minus 1. Gamma f is still contained in that, right, because we just extended them to a bigger space. And remember, x tilde is equal to the closure of the graph in x cross PR minus 1. Okay, but this vanishing locus here is already closed, right? So if I take the closure, of this, I have to take the closure of this too, but that's already closed, so we don't need to do that. And this gives us exactly what we want, that x tilde is contained in this vanishing set. Okay, maybe you want to think a little bit about why this vanishing set is closed. These functions here, if maybe we need to restrict them to an affine cover, but if you restrict them carefully to the affine cover of PR minus 1, you'll see that this is just a vanishing set of some regular functions. Okay, good. All right, so that's the end of the proof. All right, I think we're finally ready to do our first interesting example, and this is actually one of the most important examples of a blow-up. Let's look at the affine space AN, and let's blow up at the origin or in other words, I want to blow up at x1 through xn. These are just my coordinate functions. So I want to think about this so that as blowing up at the vanishing locus of these functions, right? So this is just the origin, 0 in an. All right, so what does this look like? So first claim is that actually an tilde is actually equal to the vanishing locus described in the previous lemma. So it's actually going to be equal to yi xj minus yj xi inside of an cross pn minus 1. I think maybe I won't write down all the details just because I want to get to the geometric intuition. But basically how it goes is that you check that this vanishing locus is covered by affine sets isomorphic to an that all intersect each other. And so you get that the vanishing locus is irreducible. Of dimension n. Since the blow up is also of dimension n. Right, so this blow up is of dimension n, and it's by the previous lemma, it's a closed subset of this vanishing locus. So that implies that you get equality. All right, so I'll leave you to read the details. What I want to do now is think about this map, an blow up mapping to an. So this blow up map. Okay. If we have a point A that's not the origin, then pi inverse of A is just a single point. Why? Because away from the origin, this map pi is just an isomorphism, right? So we talked about that, and we basically proved that in general. So yeah, pi is an isomorphism away from the origin. So the interesting case now is what is pi inverse of 0. All right, so let's look at that. Well, if we look at pi inverse of 0, we go back and look at these equations here. What is this 0 here? Now this is this meaning 0 in x's, right? So this will be the vanishing locus of yi xj minus yj xi contained in an cross pn minus 1, but restricted to the place where all the x's in the an, right, where the xi are all equal to 0. Okay, now if the xi are equal to 0 for all I, then all these relations here, right, all these relations become 0. Okay, and also you get just 1 point in the an. So it will just be, this will just be p n minus 1. All right, so now we get kind of an idea of what this pi is looking like. It's an isomorphism everywhere except over the origin. The fiber over the origin is just a copy of pn minus 1. So your first attempt to try and draw a picture might look like this wrong picture here, right? We have A2, and we have above that we have A2 but over the origin you have a copy of P1. Okay, so that gives you kind of an idea of what the fibers look like. So the fibers over every point is just a single point, is isomorphism away from the origin, but at the origin there's a copy of P1, a projective space above it. Okay, now the reason it says that this is a wrong picture is because the blowup is actually irreducible, as I think we mentioned already, whereas this picture sort of suggests that it's reducible. It suggests there's like this separate component of this P1 that intersects the A2 at a single point. That's not correct. The better thing is this correct picture over here. So I'm going to tell you about that, but let's think about this for a minute first, and then we'll talk about why the correct picture is better. So let's let L and AN be a line through the origin, and let's try to think about what is the strict transform for the blowup of L. So what is L tilde inside of AN tilde? All right, so remember what this means. This means that I blow up L at the same functions that I used to blow up AN. And or you could think about it as taking the L minus the exceptional set, so intersected with U, and taking the inverse and engender pi, and then taking the closure. So that'd be another way to think about it. You get the same thing. Okay, but what is that? Well, we already know that pi is an isomorphism away from the origin. So if we can just understand what is L tilde intersect pi inverse of 0, then we'll basically know what's going on. So let's try and answer this question. First, let's remind ourselves what is the map F. Remember, I had a map F from AN to PN minus 1, and what did it do? Well, it just takes some coordinates, the coordinates on AN, and it maps them to the chosen functions. Now the chosen functions were just the coordinate functions, so we just get this map here, right? And normally these would be like, f of x, f of all the x's, f1 of all the x's, and fn of all the x's, but the f's were just chosen to be x1 through xn. So that's what we have. So what does the graph of f look like? The graph of f just looks something like this. You have all the sets of pairs, x1 through xn, and then the same thing in homogeneous coordinates. Right? They're considered as a subset of AN cross PN minus 1. Okay, with the restriction that not all xi are 0. Right? Because if these are all 0, then this map wouldn't make sense. This point wouldn't be well defined. Okay, well, let's now think of what is this graph intersected with L, where by intersecting with L, I mean used isomorphism, where this graph here is isomorphic to, actually isomorphic to AN minus this condition, right? Because just by using the projection down here, like these points here are just the coordinates on AN. Okay, so if you intersect with L, then you just get the set of all points in AN that are on L. So L, except for we have to subtract off this condition. So let's just write L subtract the origin. Okay, and then what do you get in the projective side? Now the interesting thing that happens here is if all these points lie all on the same line, then this here will represent the same point of projective space, right? You can think of projective space as parametrizing lines in AN. So let me just write the singleton set containing the equivalence class of L, right? Thinking of Pn minus 1 as parametrizing lines in AN, then L intersect the graph will just be all the points on the line except for the origin here. and then in the projective space, you'll just get the class representing the line here. All right, so that was nice. So now we want to think about the strict transform. The strict transform is just the closure here, but it's kind of easy to see what the closure is, right? We took out a point 0, so the closure is just this as a subset of an cross Pn minus 1. Okay, and now we can see what's going on here. This is just going to be class of L considered as a point in Pn minus 1. All right, so every line intersects the exceptional fiber in the point corresponding to that line, if that makes sense. Let's now look at the correct picture here in the textbook. So down here you have lots of lines L through the origin. But then if we look at the blow-up up here, all the lines have become separated. Each of them intersects the fiber over the origin. So this vertical line here is the fiber over the origin, and that's supposed to be a copy of P1. And every line down here, so this line right here goes up to this line right here, and it intersects the fiber in a single point, and that's the point corresponding to that line. And similarly, every line here intersects the fiber in the point corresponding to the line. So all the lines that intersect here have become separated in the blow-up. Maybe slightly harder to see, but also is what's supposed to be represented here is every point away from the origin is supposed to have exactly one pre-image here. So if you stay away from the origin, you just map up to some point on this little helix thing. To make this picture correct, you really should be like gluing this top line here. This top line should be glued down to the bottom somehow. Right. Okay, so this is a more correct picture. You see an irreducible space here up top, and you can see how the lines are becoming separated. You know, the wrong picture is maybe a lot easier to draw. So honestly, if I'm just trying to think to myself, I might just draw the wrong picture. But then you just have to remember that if you have like a line coming through here, it has to kind of jump up and intersect this P1 in the right place, and a different line will intersect the P1 in a different place. Okay, so that's kind of the way to think about the blowups. Okay, I think we're going to call it good for today, but we will talk more about blowups in the next lecture.